Thank you for having me. My name is Seun, and I'm the founder of Polytope Labs. Today I'll be talking about some of the research that we've been doing at labs, especially into interoperability protocols. We call it ISMP. But before I can tell you about ISMP, first we need to understand sort of the fundamental structure of blockchains. A blockchain is a state machine. You have a block, it represents or it holds some state at that block, the so-called state root. And you can think of this state as the result of applying the transactions at that block. Just some refresher knowledge so that we can get into the meat of things. So that state root is this Merkle commitment. It's a Merkle Patricia tree. And you can have all different kinds of trees, actually. You can have IEVL, and IEVL is like a base 2 tree. A Verkle tree can have an arity of up to 2,048 nodes in a branch. But really, state proofs are just Merkle proofs. So I give you a structure of a state machine. You can see that there are different states. In fact, some blocks may have competing states. But the role of consensus is to tell us what is the canonical order of these so-called states. OK, what are consensus? What's consensus? Well, since we understand what state proofs are, it's clear that state proofs are useless without consensus proofs, right? Because we see that there might be multiple conflicting states for a particular block. So consensus proofs are usually a cryptoeconomic guarantee. I know it says proof, but I think of it more of an argument that says that this series of blocks are final. In proof of work, you already understand that the argument is that these header, the longest chain, has the most work done on it, and so there really shouldn't be any conflicting blocks that should be regarded as final. But in proof of stake, it's simply the signatures from all of the so-called validators of the network. And the theoretic assumption here is that if they sign conflicting views of the network, then it gets slashed. So now we understand state proofs, consensus proofs. Let's look at ISMP. So ISMP really just means the interoperable state machine protocol, in that we only look at the state machine side of things. We're trying to bridge state machines. These state machines may live on the same consensus layer, or they may exist in different consensus layers. It's also designed to be an efficient and flexible alternative to HRMP, where HRMP requires all these channels, XCM messages. With ISMP, you have a more efficient or more flexible way of sending messages. And it's also more efficient because you're not routing messages through the relay chain. You're just sending Merkle proofs of these messages. And it provides an HTTP-like API. And this is actually critical piece of ISMP that we wanted to replicate in the blockchain space. So what that gives us is an unopinionated messaging format, right? You can put whatever it is you like in the so-called ISMP requests. You can put JSON, scale-encoded messages, XML if you're feeling masochistic. So we have post requests and we have get requests. Post requests, of course, you use that to send data. Get requests allow you to request for storage items that live in a different state machine. Of course, you can imagine the get requests are actually giving you storage proofs of these items. The initial R&D was funded by the Web3 Foundation. And really, this is how I like to think about ISMP. You give it some request, it gives you a response. It doesn't really care what else you do with it. So the request response model allows us to, like I said, exchange messages, also request state proofs. We copied the HTTP model because we believe that that is the most successful interoperability protocol, really, in the digital age, right? HTTP powers billions of applications today, and I don't think there's anything better than HTTP. Post requests allow you to send data. The thing is, though, is that ISMP modules don't actually handle state proof verification. All of that is handled by the ISMP framework. At the end of the day, the modules just get the data that was sent to them. So it's super simple from the perspective of a developer. Get requests, same thing happens. The ISMP framework will verify the state proofs and just present the modules with the data that they requested. And you can kind of see here how I present ISMP as really this analogous thing to HTTP, whereas people in the middle would have wanted to do crazy things like multi-hop routing, or now we have to incentivize relayers. But we don't think all of that is necessary. Developers should just care about sending messages, requesting state proofs. So ISMP modules are sort of the modules that live on top of the ISMP framework. They have the ability to dispatch requests to the ISMP framework, and they have the ability to receive requests from the ISMP framework that are, of course, coming from an external state machine. You can think of, so you understand the call enum as a way for users to interact with your modules, or your so-called pallets. There will also need to be this external or this separate interface that allows other applications to call into your module, right? You can think of it as like the express handlers, if you are familiar with Node.js, and how you have handlers that can get called, and that triggers some logic to be executed on your chain. For now, we support Sub0 pallets and EVM contracts. We're planning Inc. as well, but really any kind of contract environment can be supported. And you can see here that we have pallet ISMP. It has this router thing, and you can imagine requests come into the ISMP framework. It gets routed to this EVM pallet module, and then this EVM pallet module actually goes ahead to call EVM contracts that live on your chain. So this way, EVM contracts are supported by ISMP. So relaying messages is a bit of a tricky thing. Cross-chain messaging, or the need to send out messages, will typically be as a result of some user interaction. Some user calls some contract, and then as a result, requests need to be sent out. So what that really tells us is that users should self-relay, right? Because it was their action that triggered the request in the first place. Well, not really the users, but the wallets or whatever the front end they were using to interact with the contracts. So this avoids the need for dedicated relayers, so teams don't have to run a dedicated relayer and try to relay requests and then start to price in the cost of requests into their interactions. They just pay for the cost of executing the messages on the destination chain. Now, something cool about Polkadot is that we can actually introduce this signed extension that allows users to pay for execution after the transaction is executed. In this way, if the transaction was going to fund their account, then you pay for it after you get the funds in your account. That allows you to self-relate to chains that you don't have the destination fee token. Just covered this. But of course, we also provide this relayer implementation. It's called Tesseract. And you can imagine you have chain A, you have chain B. Chain A emits a request event. The relayer will pick up that request alongside the Merkle proofs and just send that to chain B, which may emit a response event asynchronously, by the way. So in the API for ISMP, it's not that we give a module a request and it has to return a response. No, the module can return a response whenever it feels like. And if a response event is emitted, then you get that response with a proof, and the relayer just sends it back. Simple request lifecycle. So we have this, but unfortunately it's closed source for now, pending we figure out public goods funding in the Polkadot ecosystem. There are other ideas for a relayer-less world. I think some people were thinking about having the collators themselves participate in the P2P networks of all these different parachains. It's not really clear how that would scale, especially in terms of networking load, or who will even pay for these messages if these collators are inserting these messages into their blocks. Like, as an inherent, then no one's paying for it. It's paid for by the chain. So these are sort of questions that are unanswered yet. So ISMP also supports solo chains because it's designed to be modular. You can actually support any kind of consensus system. We actually have Grandpa, Beefy, as well as the Ethereum beacon chain sync committee. There are other plans to add more consensus clients in the future. We have all of this. And of course, because we support Grandpa, that means Polkadot, the relay chain, Polkadot relay chain, and the Kusama relay chain can also communicate over ISMP, and this is something we'll be working on in the future. So now that we see ISMP as this cross-chain messaging framework, I also like to change our perspective and see ISMP as a synchronization primitive. What does that mean? It means if we think about this new core time and this new core model that Gav has proposed, we can see ISMP as a way to distribute work across cores, right? If you have work that needs to be done on a Parachain core, you can use ISMP to push that work to have it executed and then read the response or the result of its execution once this is done. So you can think of ISMP itself as a kind of MPC, MPMC, or MPSC, for those of us who are familiar with multi-threading and the multi-threading paradigm. You can think of them as channels. You can just use ISMP to post some work, tell this Parachain core, hey, do this stuff, and it could send you back the result. Now, a little bit of alpha leak. We're working on this bridge called Hyperbridge. it's going to be the bridge that connects Polkadot to Ethereum using this ISMP protocol. Of course, there's Snowfork. Snowfork is using HRMP, but our Hyperbridge will be using ISMP. Now, in Hyperbridge, we actually want to run the full Caspar FFG consensus protocol. This is a very expensive consensus protocol to run, and so we will need to dedicate a full core that just does processing of Caspar FFG consensus proofs. But if we have a full core doing that work, how can we read the result of this work from a more user-facing core that will just be processing, requests, responses? So you can now start to see how ISMP comes in and facilitates this multi-threaded work sharing across cores. So we have one core for processing consensus proofs. We have another core for processing requests, responses, proxying these messages to parachains or even external chains. And I just described this as well. So this is what makes Hyperbridge hyper-scalable, because you can imagine we can start to add more cores as we add more support for chains, and these cores just communicate with each other using ISMP, and they pass work across themselves. So there's a fun meme here for just describing how exactly Hyperbridge would work. If you can imagine, we have multiple cores. We just dedicate core 1, and all it does is process consensus proofs. Yeah. So ISMP is also a generalized messaging protocol. So it doesn't just support parachains alone. It actually is designed to support any kind of blockchain architecture. And in fact, we already support EVM. We have the ISMP Solidity repo. It's on our GitHub if you're interested. And this allows EVM contracts to become interoperable. They can send requests, they can receive responses, what have you. They just need a relay that will send out these requests and responses. Of course, this will allow Solidity contracts to read state proofs from any other chain, not just other EVM chains. They could also read state proofs from a parachain. So you can imagine a parachain is doing all this heavy processing, which you can't do, of course, in EVM. But then the EVM chains still have the ability to read the result of this processing. You can imagine you move your mints, your NFT mints, so-called expensive NFT mints, to a parachain, and at the end of the day, people who have these NFTs on the parachain are still able to use them on Ethereum through ISMP, whether through requests or through state proofs. All right, let's do a quick demo. Hopefully this works out well. So what I have here is okay, maybe get out of here. So what I have here is a parachain. It has the pallet ISMP installed. Then I have a local EVM chain that's running, and it also has the ISMP contracts deployed. So what I will do here is I'm gonna run a relayer that will attempt to relay some ISMP messages from the parachain side to the EVM side. And yeah, let's compile my test. So what it's actually doing is the integration test will dispatch the extrinsic, and because I wouldn't have to do anything here. We should just be able to watch it and watch it happen in real time. It says it's running. Just confirm here as well. Right, so the first thing that happens is the set consensus state, if you can read that correctly. And what that means is we set the initial consensus state for the Polkadot relay chain. So the initial validators sort of is subjectively chosen states that the consensus client can start from. We start getting our consensus messages, so we're updating the state of the parachains from the perspective of the EVM chain. I think we should see that a request has been dispatched from our parachain. It says it's headed to the execution layer. Its nonce is 1, and of course the source chain is this parachain. We should see that post message hopefully soon. This is how live demos always are. You never know if it's going to work or not. Please. I think we're still sending consensus updates. Yep, that was a consensus update. It should pick up. Okay, perfect. The relayer has seen the message. It's exactly nonce 1. The source, the destination, that's all fine. Ah, perfect. We've seen our post message. So this message actually went through 2 stages. We verified the consensus proof for the state root, and then we verified the Merkle proofs of the message itself. And our module here is just configured to emit whatever was sent from the Polkadot side, which is just a nice message, hello from Polkadot. So that works, yay. Yeah, that's about it. But let me just cover the future work. I already talked about this. We want to work on a Casper FFG consensus client. This will allow us to verify the full consensus proofs of Ethereum. We currently have a sync committee, but we're not too confident in the security, so we want to make that more secure using Casper. This Casper FFG has like 700K validators, so it's ridiculous. We actually need to use ZK proofs to make this possible. But the security of Casper FFG is very evident. It's much more secure than the sync committee. And actually has safety through slashing. Our next thing on our list is to use Verkle trees. So we currently use a Merkle mountain range overlay. In fact, I can go back and show you what is going on here. You see this multi-proof is actually a base 2 Merkle proof. So we're using the Merkle mountain range proofs here, not actually the full base 16 state tree proofs. This is because Merkle mountain ranges have much cheaper state proofs than the conventional base 16 Merkle Patricia tree. And we want to make that even more secure, or more cheaper rather, than by using a Verkle tree. So a Verkle tree actually uses polynomial commitments for proof verification. But of course, there is no precompiles for this yet on Ethereum. We're still waiting for some EIPs to enable the BLS precompiles. And I think last thing would be to make Beefy and the APK proofs work within a non-native curve. Gist of it is, instead of using an external curve for the APK proofs, we use the same curve that the BLS signatures use. And so we can put all of that into the same BLS precompiles on Ethereum, and we have the cheapest consensus proofs. No, not really we, but Polkadot will have the cheapest consensus proofs. Yeah, thank you for your time. Any questions?
Thank you for a really interesting talk. I think ISMP is a really nice addition to the Polkadot ecosystem and fits really well into its philosophy too. So we still got some time, so do we have any questions from the audience? Please raise your hand and I will pass you the mic.
But the second chain will always have to wait for the finality of the first one and back and forth.
Yeah.
So they basically, you need to synchronize them about the finality guarantees of both kind of like individual chains.
More like finality time.
Yeah, but I mean, like, if finality of ETH is, I don't know, 15 minutes, and Polkadot is, I don't know, 1 minute drop?
It's like 3 blocks.
30 seconds. So then you need to wait 30 seconds plus 15 minutes of it. Okay.
Yes. I have a question from Rob. Should be fun.
I'm not here to grill you. I'm curious, how much compute does it take to prove the ZK Casper proofs for 700K validators, and what kind of hardware and cost do you have for that?
That's a good question. So it's actually pretty cheap. And I'm not really going to go into the mechanics of the snark itself, but the paper says it takes 4 minutes to prove 1 million validator sets, like a set size of 1 million. So 4 minutes for proof time. And the thing is, though, is that we don't need to prove all of the validators at once. As attestation messages show up, we can prove their participation rates and then submit that to the verifier. So we can actually hide that proving time within the finality period of ETH itself. Yeah.
But who submits these proofs? Is there a GPU cluster that's doing them?
Oh, it's not. We can do this on CPU actually. It's we're not proving a VM. We're not trying to do a ZK VM or RISC-0 or something. It's just elliptic curve point addition, and that's pretty cheap to do. Plus, the snark itself doesn't do a lot of stuff that would make it expensive. For instance, it completely eliminates permutation checks. So the expensive part of Plunk is actually in the wiring and the constraints for the wiring. That's actually the most expensive part. So the snark circuit doesn't have this wiring. It's been designed to be as efficient as possible. In fact, this is the same snark circuit that will be used on Polkadot. And we can imagine that this is what makes it cheap.
Okay, thank you.
Yeah.
Right? Anyone else? Just a sec.
Yeah, thank you. Question is, how does it look like on chain? So, for example, I have a contract on chain A, and I execute some some method get on some other contract, and then I wait for event on the same contract with like post code, or how does it look like?
Right. I may have glossed over gets. So in the get requests lifecycle, a contract emits a request, a get request, but it doesn't need to be relayed to the counterparty chain. Instead, a relayer will observe this request and then fetch the data and the Merkle proofs for this data and just relay back to chain A. So,
I mean, how exactly contract on chain A can receive an answer?
So the relayer, the off-chain relayer will see your GET requests. They don't need to relay, they don't need to submit this request. Instead, it's an instruction to them to fetch the data from chain B, from the storage entries that you're interested in, and then return those Merkle proofs back to chain A.
Okay, thank you.
Yeah.
Yeah, hello, Sean. So my question concerns on the message passing. So in there is an off-chain relayer which actually relays messages to different chains. So it kind of have the indexing all the chains which have ISMP pallets, right?
Yep.
And also so the request, okay, in XM concept, there is you can call something using transact, right? Transact instruction. So in terms of ISMP, there is no a framework or message format for fetching something. So it's just a blob of data which correspond to something, right? So one thing is those blobs of data, the sending chain should be aware first on the okay, I need to construct some request, which actually that request can be meaningful to chain X, right?
Yes.
So it means the chain which is sending needs to have kind of pre-information about the receiving end, right?
Yes.
And how that is done.
Well, I think of ISMP, like I said, as like a HTTP abstraction. In the classical HTTP sense, you actually need to know what kind of messages a server can interpret, what protocols it supports before you as a client can send messages to this. Of course, the receiving end has to exist before the sending end, right? So the receiving end defines what kind of messages it supports, and the sending end just conforms to that protocol specification.
Okay.
Also, it's possible with ISMP to introduce this sort of transact abstraction, right? You have some sort of proxy application or proxy module. You can send it the ABI encoded call of any abstract contract that lives on its chain, right? And then this proxy module will then decode this ABI and then call the module directly as if you were trying to call it from a different chain. So it's because of this flexibility, you can actually do whatever you want. Like you can have this proxy module, or you can just message the applications directly.
Okay, and also follow-up question, that's it. So there is this concept of origin in Sub0, right?
Yeah.
So in ISMP, it's just your chain and another chain, right?
Yeah.
And the initiator of the messages can be an end user, right?
Yeah.
Maybe some computation needs some data from chain B, so the chain actually requests, right? So in terms of encoding the origin, will the origin be, will the user be also taken into consideration in the origin, or to be like just chain A and chain B, that's it, and there's no concept of a signed origin or something like that?
That's a good question as well. So if you look at the request object, there's a lot of stuff in here, but I'll just walk through them. We have the source of, no, what am I saying? This is the proof for the object. So this is the request. We have the source, some opaque bytes. This is the source chain. The applications know how to decode this. The destination chain. You have the from. This is the pallets in which this request came from. This is the to, the contract address that this message is intended for. Of course, you have the body and then some gas limit stuff. So in this case, from would be the originating application. It's the responsibility for the application to track which user initiated this request. from the perspective of the receiving chain, they don't care. They just want to know what application that they're talking to, because it's an application to application protocol, not really user to application. So, of course, when the response comes back, the application knew it sent out a request on behalf of this user, and so it will handle the response however it likes.
Okay, thank you.
Okay. In the case of EVM, are you guys building the Merkle Mountain Range tree in a smart contract, or leveraging the it gets proof RPC to extract the proofs from the storage of the contract?
From the perspective of a user that wants to interact with EVM, sure, we have to get storage proofs of the EVM contracts. Okay. But from the perspective of the EVM chain that's interacting with our parachain, we actually use the Merkle Mountain Range proofs. So the EVM contracts are verifying Merkle Mountain Range proofs. And we have a library, it's open source, Solidity Merkle trees. You can check our GitHub. It has an implementation for the Merkle Mountain Range tree, the Merkle Patricia tree, and the classic binary to Merkle tree. Yeah.
All right, thanks everyone for great questions, and thank you, Sean, for a really great talk.